Hello and welcome to my video presentation for the Bernoulli IMS One World Symposium 2020. My name is Anita Winter. I'm presenting joint work with Wolfgang Löhr. We are both colleagues from University of Duisburg-Essen. In today's talk, I would like to introduce with algebraic measure trees a novel notion of continuum trees and equip the space of binary algebraic measure trees with a notion of convergence in such a way that we result in a space which is compact. Let's start with a graph theoretical tree, say a finite tree. We can associate it with a metric measure space by letting T be the set of vertices, the distance being, for example, the graph distance, and choose for the measure, for example, the uniform distribution of the set of leaves. If we do this, then we result in a metric structure which has two important properties. First of all, the metric space is zero hyperbolic, or equivalently, it satisfies the so-called 4-point condition. Moreover, all possible branch points exist. What does it mean? That means that whenever I have 3 points, x1, x2, x3 in T, there exists a unique point C in T, such that C lies on all 3 paths connecting 2 out of the 3 points. You can see in the pictures below, in the first picture, only one property, namely zero hyperbolicity, is satisfied, while branch points do not belong. This is not a tree. The second picture clearly is a tree. The third picture explains to you the 4-point condition, which I didn't write down in detail, by just saying that whenever, or illustrating that whenever I have 4 points, the only possible geometry they can form is this quadrat like you see here. For today's talk, we would like to ignore metric distances and focus only on the tree structure. So if we have no metric structure, we are left alone with the branch point map, assigning 3 points a branch point. We say that a tuple TC is an algebraic tree with symmetric branch point map C from T to the 3 to T if the following 3 conditions are satisfied. A so-called 2-point condition, whenever I have given 3 points, which are actually only 2 because at least 2 of them are the same, then the branch point must be the point which appears double in the 3-point set. Then there is the 3-point condition, which is actually just a projective property saying that if I'm given 3 points, say x, y, and z, and I have already evaluated the branch point, and I now want to use this branch point and try to create new branch points, then I must fail, because the branch point of 2 points, say x and y, together with this branch point, gives me back the branch point. And then there's the 4-point condition, which is exactly imitating the 4-point condition we saw earlier, reflecting the fact that any 4 points span this quartet, which you see again now above. And you can see from the picture that such a quartet has the property that it has at most 2 branch points. And therefore, this is how we can characterize this. No matter which choice of the 4 possible choices of picking 3 out of 4 points I choose, say x, y, and z, this branch point of x, y, and z must be equal to one of the 3 other branch points I get from the 3 other choices of 3 out of 4 points. So algebraic trees, they behave more like these graph theoretical trees. They allow for a lot of classical notations. For example, if you want to define the path between x1 and x2, connecting them, then you just define it as being the set of all points z in T, such that z is the same as the branch point of x1, x2, and z. You can call a 2-point set x1, x2, and h if the path connecting these 2 points consists only of these 2 endpoints. The degree of x equals the number of subtree components on T once you have taken away the point x. And similar, you can also define branch points or leaves or whatever you need for your construction. An algebraic measure tree, the object we want to study here, consists of an algebraic tree together with a probability measure mu on T. For the purpose of today's talk, to end up with a compact state space, we require that the algebraic tree is separable and consists of at most countably many edges. Let me mention at this point that there are other objects studied recently which are very similar in spirit to algebraic measure trees. One of them are dendritic systems studied by Steve Evans, Rudolf Grübel, Anton Wackolbinger, which are basically rooted, ordered binary trees. And then there's the notion of interval partition trees introduced by Noah Forman, which allows even for non-binary trees. In what follows, I would like to collect in T the space of all equivalence classes of algebraic measure trees. And the question I want to answer in this video is, can we equip T with a global notion of convergence? What does it mean? Global basically means you want to study the structure of a finite number of typical points obtained by sampling, and you evaluate the structure, in our particular case here today, by evaluating the shape of the subtree spanned by my sample. For that, I need to explain to you what is the shape. Let me first restrict to the subspace of binary trees. Even more, I would like to require that my sampling measure, if it has atoms, these atoms are only on the leaves. As a preparation, I want to define a labeled M-cladogram as a combinatorial, unrooted binary tree with leaves which are labeled. More precisely, I want that there is a surjective labeling map which takes the numbers from 1 to m and sends them to the set of leaves. I do not require this labeling map to be injective. Therefore, it is possible that you have multi-labeled leaves. As you see in the picture, this is reflecting the fact that if you pick a finite number of leaves, that you might have repetition in your sample. So let's define now the tree shape spanned by a sample. For that, we start with a finite number, say m points. We require that these are non-branch points. This is almost surely satisfied for every sample because we require that the atoms are only on the leaves. And then we define the tree shape spanned by these m points as the unique labeled M-cladogram, which satisfies 3 conditions. First, the leaf set should consist exactly of the leaves in our sample. Secondly, the labeling map should be canonically in the way that we send I to the leaves sampled in the i's round in our sample. And last but not least, there is a technical condition, SH3, which ensures or tells us what to do if we have sampled 3 points which are lying on a line. Like as you can see on the left-hand picture, in the 3rd and 7th and say 3rd round, we have sampled 3 points which are on a line. If you look at the tree spanned by them, then this doesn't really look like a binary tree. In order to obtain a labeled cladogram, what we need to do, we need to have a rule which tells us that we have to push 7 away from this line. As you see in the picture on the right-hand side, this is what is guaranteed by condition SH3. Okay, so now that we know what is the shape spanned by a sample, we just say that the sequence of algebraic measure trees, binary algebraic measure trees, converges in sample shape to a limiting binary algebraic measure space if all m sample shape distributions converge. And our main result, as I said in the very beginning, is that we were able to show that the space T2 with the sample shape convergence is compact. How does one prove such a result? The proof uses correspondence to subtriangulations of the circle. Let me start with a very formal definition. A closed subset C of the closed unit disk D is called a subtriangulation of the circle if and only if the following 2 conditions hold. First condition, the convex hull of the set C minus C consists of a disjoint union of open interiors of the triangle. If you look at these 5 examples I have drawn you, these are all subtriangulations of the circle, then you will see that except the picture number 4, everything it's convex, so the convex hole minus C, it's empty, and the first condition is an empty condition, while in the picture number 4, which by the way is the subtriangulation corresponding to Aldo's CRT as an algebraic measure tree, you see all the triangles appearing once you take away the black lines from the unit disk. There's condition number T2, which says that C is the union of non-crossing straight line segments whose endpoints are in the circle line S. This is satisfied in all the pictures. As you can see, there might be some degeneration, like in the first picture, where the line is actually just a point. But other than this, I think it's a simple condition. This condition was missing in an original definition of Aldous in 1994, but is needed to guarantee that all the branch points exist. If T2 fails, then it's not always possible to assign a subtriangulation with an algebraic measure tree. And this is what we want. So we now collect in calligraphic T the set of all subtriangulations of the circle, and then it's standard to conclude from the compactness of the unit disk that T must be also compact once it is equipped with the Hausdorff metric. And what we want to do and did is to transport this compactness of calligraphic T to our space of binary trees. And for that, we proved the following deep result. We were able to construct a surjective map which takes any subtriangulations of the circle and maps it to an algebraic measure tree in such a way that this map is continuous once calligraphic T is equipped with the Hausdorff metric and T2 is equipped with the sample shape convergence. And it's exactly this continuity which allows you to conclude that also T2 must be compact. If you are interested in more details or also in the motivation behind constructing such a compact state space, please see us in the live session. Bye for now.